All right, here we are, chapter 5, gases. Let's get into it. A gas is any physical substance that has D, no definite volume or shape, and expands to fill its container. That's going to be letter D, and that's going to be on page 71. According to the definition and formula for pressure, if the area increases, pressure will decrease. That's going to be on page 72. A little metaphor for that, let's say you have a bunch of people, there's a whole bunch of people. They're all in one room, they're all crowded. You can look at that as pressure. People are gonna get uncomfortable. But let's say they're like, hey, there's a door right here. You can go into this door, and then there's 2 rooms. You can split it up so that there's less pressure, because people is a good reference for molecules. So if there's molecules into one confined space, and all of a sudden that space opens up, some of these molecules can go over there, and that will decrease the pressure. Right? Even though that's the same amount of molecules. So there's 1, 2, 3, 4, 5, 6, 7, 8, 10. Instead of 10 being in one section, now you can have 5 over here, 5 over here. By opening up the area, you've decreased the pressure. All right, number 3, according to Pascal's law, if a piston applies pressure to a fluid in a sealed cylinder, the pressure will A, be applied equally and undiminished to all surfaces of the cylinder. That's page 72, equally and undiminished, the keywords there. Moving on to number 4. Critical pressure is the B, minimum pressure at which gas at its critical temperature can condense. Page 73, gas to liquid. Gas to liquid, that's on page 73. Condense is what happens when a vapor turns into a liquid. Condensation, raining, stuff like that, moisture, gas to liquid. So that's gonna be B. All right, next, 5, the pressure, the pressure on a substance, the pressure needed to bring about change of a physical state. So it's higher and lower, letter B. That's gonna be on page 73. So I'm gonna read, I took a picture of that. Oh no, I didn't take a picture. But if you go to page 73, they explain it pretty well. And I will, there you go. So let me try to explain the blank pressure. The higher the pressure on a substance, the lower the temperature needed to bring about change. Yeah, so that's kind of what HVAC is you're altering the pressure of things so you can alter their temperature. You can go more in depth, but that's gonna be like a majority of what you're actually doing. All these calculations are just for you to understand what's happening. All right, see what we got here. Blank law states that blank law states that a volume is held constant. Temperature varies directly with pressure. So if you look at it, you got Boyle's, you got Charles, you got Dalton, you got Gay-Lussac's. So Boyle's, if you go to page 78, it's inverted. So that's not correct. See, ours says varies directly. This one is invertedly, varies inversely. You don't want that. That's Boyle's, that's gone. Dalton's relates more often to gas. So that's gonna be a different one. So all that's left is Charles and Gay-Lussac's. Now when Charles and Gay-Lussac's, they're both constant, except Charles is constant pressure, Gay-Lussac's is constant volume. So if you look at that first line, it says law states that volume is held constant, temperature varies directly with pressure, constant volume. So now that's the difference, and that's why it's D, and that's on page 78 through 79. Now Charles, only difference that, so one thing they do agree on, Charles and Gillis, is that temperature and pressure rise together directly. That's going to be brought up so many times on your test. Pressure and temperature go up together. And you can prove that, like, think about when you've been in a car in a hot day and the windows are rolled up. As that temperature rises, so does that pressure in that car. When you're cooking something and the pot is on, you put the pot on the water, you put the top over it. As that temperature increases, so does the pressure inside the top, to the point where the pressure will start to blow off that top a little. It'll start bubbling out and moving the actual metal top on its own. Increase temperature, you'll increase the pressure. Increase the pressure, you'll increase the temperature. All right, number 7. Blank law states that the confined mixture of gases, the pressure of each gas must be added to calculate the total pressure. That's gonna be Dalton, that's on page 80. So the key word was confined mixture of gases, find that on page 80, C, Dalton. According to the combined gas law, this is on page 80, If the pressure of a gas is held constant and its temperature is increased, then the volume of the gas must increase. We just talked about it. Increase proportionally. Temperature goes up, pressure goes up. All right. Number 9. That was B, increase. Number 9. A saturated vapor will condense if the blank. Pressure is D. Pressure of the vapor is increased and the temperature is decreased. That's page 80 to page 81. All right. A cooling effect can be generated through D, all the above. That's on page 81, and there's a paragraph for each section. A paragraph for air exchange, a paragraph for pressure change, a paragraph for state change. All the above. All right, critical thinking. Number 1, determine the pressure applied to a 5x5 area by 525 pounds of force. Show your calculations. So this is on page 72, this formula. So what we're gonna do is P equals F over A. P is pressure, F is force. A is area, F is force. We were given, it was 525 pounds. A is area, which is the 5x5 inches. When we do it over here, we're not gonna multiply 5 by 5, we're gonna take 5 inches squared. That's the number we're gonna use. So we're gonna divide the 5, just the 5 by itself, because it's 5 inches squared, just the 5, and we're gonna divide it into that. And you're gonna get 105 PSI. Make sure you do the big number first. Big number gets into that. All right, let me make sure. Sometimes I do things without realizing it. Let me see. 525 divided by 5, 105. All right, make sure you do the big number first. And you got 105 PSI, that's the answer for that. And keeping it going, where's the questions? I just lost my own, I think. Give me 1 second. All right, number 2, explain how the principles of Gay-Lussac's law applies to normal operation of forced air, of air-conditioned system. How does the system move heat and produce a cooling effect? All right, so I put down that pressure and temperature go up proportionally, and as pressure increases, temperature increases. Now, and here's an example. I'm from page 81. Blowing warm air across cold pipes to cool the air, because heat transfers from warm to cold. So what happens is, like if you were to put like a warm can of soda in the refrigerator, and everything temperature is relative, right? So you put the warm can in the refrigerator, what's actually happening is the warm air, you think that the cold is going into the can, but what's actually happening is the warmth is leaving the can and going into the cold environment. It's just like an inverted way of happening. Like sort of like you know, back in the day you eating oodles and noodles, and maybe you dropped in some ice cubes to cool it off, or maybe you blew on the soup, and you were like, you blew on the soup, and what's happening is you think you're cooling the soup by blowing on it as if you're inserting cold into the hot soup. But what's actually happening is the heat from the soup is leaving the soup and trying to cool off the air. So it's kind of like inverted in a way. All right, so number 3, I'm not a professional, just a student. Please refer to your teacher or instructor. Number 3, let me get that question. If air became trapped inside an air conditioner's condenser, how would this affect a condenser's pressure and temperature? Explain why and include which gas laws are at work here. I'm gonna go with Charles' law and Gay-Lussac's law, both of those laws, because both temperature and pressure increase proportionally with each other. The only difference is Charles is constant pressure and Gay-Lussac's is constant volume. But that same increased temperature, increased pressure, they both agree on that. That's gonna be on page 78. And I put, this one was with the help of Google, because I wanted to formulate it as best as possible for you, to make sure that I had it right. When air, and I needed help, when air gets trapped in the compressor, it increases pressure, which will then increase temperature. Because if air is getting into the compressor, which would be where it can damage your compressor, that's a very bad day. And that's what's happening. Air gets trapped, increase pressure, increase temperature, and it's also going to increase the workload of that compressor, which will lead it to burning out. All right, number 4. How would an air conditioner's pressure and temperature values be affected if it was operating an ambient temperature of 7 degrees Fahrenheit and that temperature rose to 100 degrees Fahrenheit? Remember that a temperature difference is used to cause heat transfer between refrigerant and ambient air. Which glass laws would be in effect? Explain how that would work. They would affect systems operating high side. Explain how that would work. They would affect the system's operating values, high side and low side temperature and pressures. All right, so I wrote, okay, number 4, Charles law. And let me look up something really quick, because there's another law. I just want to make sure that what I wrote is correct. Idealized clause. So I do agree with Charles laws. And then for this one, I did look it up on the Google. They also said Amat's law. So I'm not sure if they're talking about Avogadro, but I'm gonna stick with Charles law. And I agree with it. I believe that once again, when you increase the temperature to increase the pressure, that increases the workload. And it's also going to increase the pressure on both the high and the low side, because something could still be low side and still have the pressure increase. It's just the other side, it just has even higher pressure. And some of these critical thinkings, they're very hard. So even my multiple choice questions could be incorrect, but understand that when it comes to critical thinking questions, it's going to be even a higher probability that I may be incorrect. But I'm doing my best.